Given a sequence such that a1 is smaller than a2, smaller than a3, and so on, and let them be positive integers, such that a of 2n is equal to an plus n, for n is all natural numbers. It is known that if an is prime, n must also be prime. Find, with proof, a of 1993. So before starting the proof here, let's just get an intuitive sense of how this question is. We're given that a2 n is equal to an plus n. So of course we can first outright that a of 2, assuming that n is 1, is equal to a1 plus 1, being at that. And now we can see we can get a4 here. a4, we just sub in a2 here, plus 2. And then we can sub a2 back in because we have a2 as a1 plus 1. So we have a1 plus 3. But then we notice something here, that a2 is strictly smaller than a3, which is strictly smaller than a4, by the question given. And notice that we can sub in a2 and a4 into here. So we get a1 plus 1 smaller than a3, smaller than a1 plus 3. Now notice that only here a1 plus 1 and a3 plus 3. So that means a3 by the squeeze theorem is going to be a1 plus 2. And this works for everything, every odd integer, since you can always get an even one. And if you have 2 even on the side, you can always get the odd one in here. So let's do it with 5. We know that what a4 is a1 plus 3, and we can figure out what a6 is. a6 is just equal to a3 plus 3. And we already know what a3 is. a3 is a1 plus 2, which is equal to a1 plus 5. And we can squeeze this in. We can a4 smaller than a5, smaller than a6. And subbing it back in, we get a1 plus 3, smaller than a5, smaller than a1 plus 5. And by the squeeze theorem, we would get a1 plus 4 is equal to a5. And you realize why this works is because these all have to be integers, and for a5 to be an integer, this has to be plus 4. Now that I wrote everything down that we found before, we can intuitively see that this question seems pretty simple. Right? It's just a1 plus n minus 1. And that would seem like the closed form, although we haven't proven it yet. So intuitively, a of 1993 is going to be equal to a1 plus 1992. Okay, now that we have the intuition set, we can begin our induction proof, which the proof is that we want a of n is equal to a1 plus n minus 1. And we got this formula by intuitively looking at the solutions that we have. And now to start the induction proof, we can start off with the base case. And we can start off with a1 is equal to a1 plus 1 minus 1, which is a1. And a2 is equal to a1 plus 1. And we know that this is true as we did this before. We found out that a2 is equal to a1 plus 1. And a3, we can write another one, for example, a1 plus 2. This is true, as we did it before. And now we can start off with our induction step. Now to start our induction step, we can assume that this is true for some k, and we want to prove that this is also true for some k plus 1. And we start off with ak is equal to a1 plus k minus 1. And from the question, they gave us that a of 2n is equal to an plus n. So we could write this in terms of k. So we have a of 2k is equal to ak plus k. Now we can sub in ak into this equation here. We get a of 2k is equal to a of 1 plus 2k minus 1. Now if we were to look at the inequality, we get AK smaller than AK plus 1, smaller than so on, to A of 2K. And note that this here, there are K terms. Now if we were to sum in these two equations into here, we would get A1 plus K minus 1 smaller than AK plus 1 smaller than so on, smaller than A of 1 plus 2K minus 1. And there's still K terms. Since there are only K terms in this inequality, and we are given A1 plus K minus 1 as our first term, and A1 plus 2K minus 1 as our last term, and we notice that the first term and last term only differ by K, and so that means the difference between each one is only going to be 1. And so we get AK plus 1 just is equal to AK plus 1. And we can evaluate this as summing in AK as in terms of A1. We get A1 plus K. And this proves our induction hypothesis, so that AN is equal to A1 plus N minus 1. Now that we solve our induction problem, we have this inequality here that A1 is smaller than A1 plus 1, smaller than A1 plus 2, and so on. We want to know what A1 is, so that we can find A of 1993. Let's let A1 equal to 1. We get 1 smaller than 2, smaller than 3, smaller than so on. And we notice that here that every prime number, n, is equal to an. As, for example, a of 3 is just equal to 3. So that means every prime number, n here, is also going to be prime. So that satisfies the question that is given to us. That if an is prime, then n must also be prime. Now that we found out that if a1 is equal to 1, then we would get that this is true. So let us assume the case that a1 is not 1. Let's assume a1 is greater than 1. And let a1 be some value k, where k is greater than 1. And this inequality here will just turn out to be k is smaller than k plus 1, smaller than k plus 2, and so on. And now we have two cases here. Is that either k is even, or k is odd. And in this case, if k is even, we have case 1 here and case 2 here. Let's just say that k is even, so we can label k as even as e. Let's just say e is some even number. And this, let's just write this inequality as a sequence. We have e odd, let's just write o as odd, e, o, and so on. And case 2 is going to be odd, even, so on. Now if we consider case 1, that k is even, we notice that an is prime if n is on some even n. As all primes, except for 2 is a special case, is odd. So that means an has to be an odd integer. And the only way for that to happen is that if n is on some even number. And now we can lead this to a contradiction. We know that an is equal to k plus some even number n. And if we were to write this an, we know that an is odd, and k is even, and n is even. we get to the contradiction, as even plus even is even, and odd is just odd. There's no way that this could be equal to each other. So that we know that case 1 here, if k is even, this inequality will not have a solution. Now if we consider case 2, that k is odd, notice that an is only going to be prime if n is some odd integer. So we can write this as an is prime if n is odd. And we can write this as an equal to k plus n. And an is going to be odd. So odd is going to be here. And we have some odd k here. Plus n is going to be odd, so odd. And we notice that this wouldn't work, as odd plus odd is always going to be even, and even can never be equal to odd. So case 2 is that k is odd is not going to have a solution. So now that we know for cases that a1 is greater than 1, the cases won't work, as they prove to be a contradiction. So that means that a1 has to equal to 1. And basically we're now down the question. We can write a 1993 as a1 plus 1992, which is equal to 1 plus 1992 is equal to 1993. That's it for the question. Hope you guys all enjoyed and learned something new. And I'll see you guys next time. Bye.